I grew up on a family fruit and vegetable farm in northeast Ohio in the snow belt south of Lake Erie. So in our area we get anywhere from 40 to 45 inches of rainfall a year, and of that we get about 90 to 120 inches of snow. Or actually, I need to rephrase that. We used to get snow, and that started changing, I don't know, probably 10 or 15 years ago, and the last couple of years we get several feet of snow at the most. In addition to, so we were growing fresh market fruits and vegetables. Our primary crops were tomatoes, zucchini, cucumbers, and cantaloupe. And my father was also the distributor for all the local inputs, fertilizers, seeds, equipment, pesticides, etc. I was a licensed pesticide applicator when I was 16, and I was the first, we were often the first in the area to try out new technologies, new products, and then make recommendations to our growers on how well they were working for us. And almost without question, we were the most intense users of chemicals in the community and in the region. Then in the early 2000s, 2002, 3, and 4, we had a 3-year consecutive period that we lost over 70% of our crops to a number of different diseases and insects that we were not successful in managing with pesticides. The big one on the cucurbit crops was downy mildew and powdery mildew. So it seemed no matter what fungicides we applied and how intensely we applied them, we were in that several year period, we were on a 5-day fungicide rotation where we would spray a fungicide every 5 days. And we're rotating different chemistries, rotating different products, and we still had significant crop losses. Then in 2004, we started renting a field from a neighboring farm that bordered right up against one of our own fields. So there used to be these 2 long, narrow strips that were being tilled and planted up and down the slope. Now that we were farming both of them, we switched the direction that we were tilling and planted across the field border. We planted that field into cantaloupe, and at harvest time, on the old soil that we've been farming for the prior decade that had the intense pesticide applications, 80% of the leaves were infected with powdery mildew. And on the new soil, there was no powdery mildew. There was not 5% or 10% leaf infection. This is unbelievable. I'm going to go on a warpath here. There wasn't 5% or 10% of the leaves infected. There was 0. There was this clear knife line right down through the center of the field. And that experience, this was all the same variety, it was planted the same day, had the same fungicide applications, but we got 2 completely different results. And I wanted to know, what are the differences between these 2 plants? And over a lot of study and research and having some exceptional mentors over the next couple of years, I learned that plants have an immune system much the same way that we do. They have the capacity to be completely resistant to diseases and insects when that immune system is supported with the right nutrition and with the right microbiome. Just the same as our own immune system needs to be supported with the right nutrition and with the right microbiome. And that then led to us completely changing the way we were farming. By 2006, we had discontinued all the use of pesticides. And my brothers are still running the farm today and still completely pesticide-free. That then led to us starting to do consulting work for other fruit and vegetable growers, helping them make the same transition. And on this pathway, I realized that when we grow really healthy plants, you can't stop yields from increasing. You can't stop yields from happening. And I realized all of a sudden that the way we have approached agronomy historically for the last 60 or 70 years is we have focused on balancing plant nutrition with a single goal in mind, and that was to increase yields. How can we balance nutrition? How can we balance fertilizer applications to produce the highest yield possible? So even today, the way we commonly measure fertilizer applications is takes this many pounds per bushel to grow a crop. Well, we now know that that's not true. We've known it's not true for 30-some years, but it's still an established metric. And so our approach to plant nutrition changed very slightly and a lot all at the same time. And the approach was to say, how do we balance plant nutrition to produce resistance, disease and insect resistance, and to produce yield at the same time? All of a sudden, when you start asking that question, then that produces different answers, and you start looking at balancing nutrients differently. Like the conversation I had this morning very quickly, I have erased it now, But when you understand the connection, the interactions between vegetative nutrients and reproductive nutrients, all of a sudden calcium becomes a whole lot more important. And it's quite something for us to realize, you know what? Calcium can drive the same type and volume of vegetative growth as nitrogen can. So why are folks not selling calcium? Oh wait, calcium is cheap. You can buy it in the form of limestone or gypsum. And there's the part of the answer to the problem. So our approach to agronomy and the way that we manage plant nutrition is all based on the same sciences that mainstream agronomy uses today, but we're simply asking a different question. Instead of focusing on only increasing yield, we ask the question, how does nutritional balance need to look to increase disease and insect resistance and plant health? And when you do that, you can't stop the yields from happening. So part of this pathway for us was in 2011, we started using plant sap analysis. And Chad talked about it a little bit this morning. I'm not going to go into any detail about what plant sap analysis is. But the way that we arrived at using plant sap analysis, there's an interesting story here. When I was studying plant nutrition and disease resistance, I was able to find a lot of literature in the peer-reviewed literature describing how plants should be resistant to different types of diseases based on different nutritional profiles. So for example, on powdery mildew. Powdery mildew in cucurbit crops like melons and cantaloupes and cucumbers and so forth, I can point to 40 different peer-reviewed published papers that say that there is a correlation between the presence of powdery mildew or powdery mildew susceptibility and manganese levels. The literature all says it's there. But we were using plant tissue analysis, dry matter-based tissue analysis, and we could not find the correlation. There was no correlation between tissue analysis manganese levels and powdery mildew susceptibility. And I found this very frustrating. And after multiple conversations with different advisors and mentors, the conclusion was that the test was so inaccurate that it couldn't accurately predict whether the crop was susceptible or not. So that then led us to plant sap analysis, which had been developed in the Netherlands and was only being used in the Netherlands at that point. And in 2000, we started testing it in 2011. By 2013, we started using it on all the farms that we were working on. And at the end of the 2013 growing season, I gave presentations at several different conferences, and I said publicly that I believe sap analysis will completely revolutionize the laboratory analysis, the agronomy laboratory analysis business and agronomy, because it gives us so much better information than anything else that is out there. And here we are 10 years later, and that has not happened for the most part. And I'm pretty intrigued about the why of why that has happened, and I'm going to tell you why that has happened. But before I go there, I want to tell you about the success that we had with sap analysis and some of what we learned with it. So, typically when you take a soil analysis or a tissue analysis, the thought process is fairly simple. An agronomist or a consultant pulls the sample, sends it into a lab, brings it back, and says, oh, you are low in X, Y, and Z, you need to apply this many pounds of this and this many pounds of that. It's being used fairly effectively as a sales tool. As a sales tool, you measure and you apply whatever is low, with very little consideration given to what might be excessive. And sap analysis, a couple of things happened. During the 3 years that we tested it in 2011, 12, and 13, I became really excited because there was a very clear correlation between nutritional profiles and disease resistance and disease susceptibility. In fact, on crops that we have some experience with, we can actually predict disease and insect susceptibility based on nutritional profiles. So I know that if you have challenges with spider mites, your crop is going to have low levels of sugar in plant sap, and it's going to have high levels of ammonium and probably low levels of molybdenum. We know that because that's the profile where spider mites show up. So I'm just giving you those as a couple of examples. So I became really excited by the potential of this technology to be able to use it to prevent diseases and insects by balancing plant nutritional profiles. I could give so many examples of how this plays out in practice, but what I can say in a very simple overview is that excessive nitrogen applications and excessive potassium applications, the way that agronomy has been framed is you take a test and you add what's missing. And that is based on a law that Justus von Liebig first formulated that he called the law of the minimum. And the law of the minimum, I'm sure all of you have seen presentations where you see this barrel with the broken off staves. And it says that the nutrient which is in the least supply is what is going to limit your crop. You know, I've never yet seen a barrel that included water and carbon dioxide. But that's another conversation. But there's another law that contrasts with this, which is the law of the maximum. And the law of the maximum says that it is the nutrient which is in excessive supply that creates a deficiency of something else that is the greatest yield limiting factor. And SAP analysis brought that home for us very clearly, because all of a sudden we started observing that when we put on a potassium application, that really limits calcium absorption, and it limits manganese absorption, and it limits boron absorption. All of a sudden, we're observing, and this sounds crazy because it's the exact opposite of everything we've been told for the last 40 years. But potassium applications at the wrong time will cost you yield. In fact, potassium applications at the wrong time will cost you a lot of yield, as much as 20 to 30%. So who ever heard of potassium applications causing a yield drag? You never hear that. But yet we see it all the time because we're looking for it, we're paying attention, and we're actually, with the SAP analysis, we're actually measuring what the plant's actual potassium requirements are. So I don't even know how I got started going down this rabbit hole, but the key point that I want to make is that there is this perception that regenerative agriculture is more expensive. And in our experience, particularly recently with commodity prices recently, that has not been true historically, and it becomes even less true as time goes by. Because in many cases, some of the biggest changes that we make on farms and some of our biggest recommendations are not to add more of this product or add more of that, but they're to add less nitrogen, or add it at a different time, add potassium at different times, add more zinc, manganese, whatever the case might be, and address the factors that are actually going to produce an economic crop response. So, that's my pitch. If you haven't decided to work with AEA yet at this point, after being out in the fields this morning, I'm not sure what's going to convince you. You know, I have this joke that I've used on occasion that people really like. I talk about, when we think about agronomy and plant nutrition and disease and insect interactions, it's very common to think about them in terms of chemistry and biochemistry, because that's what we've been taught, that's what we're familiar with. But in reality, all these living systems are electrical. Like plants are electrical antennas that are plugged into a magnetic grid, and plants and insects actually communicate in the electromagnetic spectrum. There's some fascinating research on this where flying insects, can detect unhealthy plants in the infrared spectrum depending on temperature and humidity levels at a distance of up to 1,700 yards. That's about a mile. It is a mile. So they actually can determine which plants are healthy and unhealthy at a distance, and they are more attracted to unhealthy plants. Isn't that fascinating? But what that means is, and the reality is, all living systems are electrical. Even the Amish are electrical. You can't avoid it. Yeah. A few laughs, but you guys are way too laid back. You're way too laid back. Yes?
So, I know there's limitations to soil testing, especially conventional methods of soil testing. I know there's limitations. But are there indicators you can even see from a soil test that will show you what types of weed pressures you'll have? And I know there's the book, When Weeds Talk. I have that copy. It's fabulous. But is there something else besides that?
So, I was asked to talk about this topic last year at the Acres Conference, and we actually did a webinar on it. That's actually something that I wanted to talk about. Is when we start talking about these regenerative agriculture ecosystems, there is so much information that is available now that wasn't 15 years ago, or that was buried 15 years ago when I started. And we've tried to make that information available. How many of you listen to the podcast? Okay, a number of you do. How many of you listen to our webinars? Much fewer. Guys, you're missing out. So, what's the difference between a podcast and a webinar? PowerPoint. Well, the difference is that on our podcasts, with one or two exceptions, I'm interviewing other people and trying to draw out their experiences and their knowledge and their information. And on a webinar, it is, historically it's often been me, but going forward there's going to be more of the other AEA team members as well, where we're giving a presentation about all the things that we have learned on a specific topic. So we have webinars on nitrogen management. So the conversation we had this morning about nitrogen application and nitrogen management. We have webinars on sap analysis, and we also have a webinar on the actual useful information from a soil analysis, and what actually works and what doesn't. So go to YouTube, check out our webinars. The information is all there. So we understand that all different plant species thrive in different soil types and different soil environments. A soil that is optimally balanced to grow alfalfa is not a soil that is optimally balanced to grow blueberries. They have completely different nutritional requirements and completely different microbial requirements. And that's obviously an extreme example. There's a whole spectrum of ranges here. But when we think about a soil type requirement for a specific plant, it is not just the nutritional requirement. We're not just talking about pH and calcium, potassium, phosphorus levels. There is also the microbial balance requirement. What's the bacterial population versus fungal population, and types of bacteria and fungi. And if you have soil, this same concept holds true not just for our domesticated crops, but also for the plants that we call weeds. So if we have a soil that dominantly grows one particular weed species, such as bindweed, there's a specific microbial profile and a specific nutritional profile that favors the development of bindweed. And by the way, it has nothing to do with the presence of seeds or the presence of rhizomes. Because why is it that we can have one field that is just loaded with bindweed or with quackgrass or whatever the case might be, and the next field right beside it is perfectly clean? There is no question that there is seed transfer and seed crossover, and yet the population pressures are completely different. And it's because of different nutritional profiles and different microbial profiles. So now you want to know what to do about bindweed. And you're going to have to wait on the answer for that question, because I don't know.
How long do I have to wait?
That remains to be determined. Yeah. What major problems would you like to solve that would have a big economic impact for you and your farm? Compaction. Yeah. That's a good one. Any major insect problems or reproduction problems? Yes. Did I see you raise your hand? No, I didn't. No, you're afraid. You're afraid of You're afraid of raising your hand? Yes.
Hay production and armyworms.
Armyworms, the bane of the South, aren't they? You know, I was actually, I started just a couple days ago doing some research on armyworms to try to understand what is different today from a couple of decades ago. Because decades ago, depending on which point in history you're talking about, you can read about swarms of locusts and all kinds of, I shouldn't say all kinds, but a number of different pests that were pests on a widespread regional scale. But why armyworms now? There's no record of armyworms being a significant pest historically, at least not that I was able to find. And what I've been able to find so far is that armyworms, while they are in the soil, while the eggs are hatching and while the small pupae are in the soil, they are fed upon by beneficial nematodes, and that our nematode populations across large swaths of agricultural land have dropped to such low levels that they are no longer grazing on the armyworm population in the soil, and that's why it's such a widespread problem over such a large area. So it really comes back again to soil biology has shifted and is different from what it was a couple of decades ago. Yeah. All right, so let's talk about compaction. Here we are. What types of, how deep?
Heavy clay, not clay, but just black land, central Texas.
Okay.
From Dallas to Austin is kind of what they call the blackland prairie.
Okay.
And it's, you can stick a penetrometer all the way into the handles when there's moisture.
Right.
When it dries out, it's like concrete, and then, cracks open up and people talk about losing screwdrivers in the cracks. Never seen them.
Yeah.
We've lost small kids up here. Yeah. Put snowshoes on your kids so they don't fall in the cracks. But yeah, it's a real problem in Texas because we get dry here in the summer. That's just the way it is.
So has the problem gotten worse than it was historically?
I think so. I think a lot of it's probably calcium and magnesium being out of balance.
Mm-hmm. Do you have good aggregate structure? Do you have good crumb structure?
It's hard to say because when it's compacted, you can't even get a shovel. And once it dries out, you can't get a shovel.
What proportion of this land in this region is being tilled? Actually, let me ask a different question.
Well, in most of central Texas, as far as I can tell, is still full tillage.
Mm-hmm.
But even in land that's been in pasture, it was probably farmed in cotton.
Right.
But it's maybe been in pasture 30 or 40 years. And you still get this just concrete. So,
how much of it is exposed to the sun during the summer?
In pastures, not much.
Not much. You still get the same. All right.
Now, and then I'll add this. When you walk on it, when it's wet, your feet will get that big around. It is sticky. And that leads me to think there's a magnesium issue.
That's a carbon problem, where soil will only stick to your footwear when it's wet when it does not have enough carbon. Obviously, calcium-magnesium ratios can exacerbate that and make it a whole lot worse, but it really comes down to organic matter. And we were having a conversation when we were out in one of the fields about compost and how compost is this nebulous word that there's this infinite variability. You can have 1,000 different types of different material that are all called compost, and kind of the same thing is true of organic matter. But once you have enough microbially active carbon and you have the soil microbial community forming good aggregate structure, good crumb structure, then that sticky boot problem tends to disappear on even the heaviest soils. And I don't have experience with the black soils here, but I do have experience with the clay soils in the Red River Valley. And that'll also produce 30-pound boots pretty easily. And when we start, and those soils have CECs of about 40 to 45 and about 35% base saturation magnesium and about 20 to 25% base saturation calcium. So it's actually inverted. They have more magnesium than they do calcium on a percent base saturation basis. And because it's 40 to 45 CEC, it's not economically justifiable. You can't afford to put on enough truckloads of limestone to fix that problem. It's just not economically viable. The solution is carbon. If you build organic matter, you can actually have softer, looser soil without fixing or without completely fixing that calcium to magnesium ratio problem. Gary Zimmer used to describe the story of how a farmer from Australia gave him a soil analysis that had 40% base saturation magnesium. And Australia typically has soil types that also crack wide open as what you're describing. And Gary's comment was, he said, "Wow, this soil must be incredibly hard." And the farmer said, "I don't think so." And they visited the farm a little while later, and Gary described it as walking on a sponge. He was able to build his organic matter to 6% organic matter content, and that fixed the calcium to magnesium ratio and the stickiness problem. So ultimately where it comes down to, the next question, the follow-up from your question is, how do you get carbon into the soil profile? And this is actually an important topic, and one that I want to talk about a little bit. I made the offhand comment when I was talking about the barrel with the broken off staves and the law of the minimum, that I have yet to see one of those barrels that includes carbon dioxide. The two nutrients which limit plant crop productivity the most frequently, the most widely, are water and carbon dioxide. It's not calcium and magnesium and nitrogen, phosphorus, potassium. It's water and carbon dioxide. So water, we all know, it's a given. And we could talk about that for a while as well. Actually, I do want to talk about water use efficiency, because this is an important topic here in this part of the country. The water requirement for a certain amount of growth can change by as much as 50% based on a plant's, the type of nutrients that a plant absorbs. So if I say that differently, I can say that you can cut the water requirement of a crop by half to get the same yield when you manage nutrition differently. And I'll talk about that in just a moment as well. But before we go there, I want to talk a little bit about carbon cycling. So everyone talks about producing high organic matter content soil that we want to have, that we want to sequester carbon, build carbon in our soil profiles, and develop lots of organic matter. And the obvious next question is, well, what's the best way to do that? Everyone talks about growing cover crops and having diverse crop rotations and adding humic substances and adding compost. But they all miss the point. The point is that the level of plant health determines how much carbon is added into the soil profile. So this could be, I can expand this conversation, and I'll try to make it as concise as I can. But let's say that this pool of carbon represents 100% of what a plant produces during its entire lifetime. From the moment the seed was planted until the crop was finally harvested, this represents 100%. Now, if you're growing a reproductive crop, like grain, corn, small grains, so forth, the literature tells us that this total pool is divided into 4 quarters. You have 25% of it in plant biomass. You have 25% of it in grain, the seed. You have 25% of it in root biomass. And you have 25% of it in root exudates. But there's a key qualifier here. So actually, this starts becoming really interesting when you convert this from percentages into actual pounds. So just for the sake of conversation and easy math, we'll say that each of these quarters represents 1,000 pounds an acre. And that's obviously a very low number, but works for our purposes. Now, the next interesting part comes in, and that's the efficiency with which each of these proportions is converted to stable humic substance in the soil profile. The research says that 70 to 80% of plant mass is lost to the atmosphere through oxidation and so forth, and so you only get, at best, in the neighborhood of about 20% of this gets stored into the soil, so that gives you 200 pounds. Root mass is the second most efficient, and here you get as much as 60% stored as organic matter, so that gives you 600 pounds. Root exudates are the most efficient, running about 75 to 80%, so that gives you 800 pounds. And the grain is obviously removed, so that's a complete negative. All right? There's one major qualifier here that I didn't talk about. And this is plants which are very healthy and photosynthesizing very well. And that is not most crops. The average crop looks like this. First of all, you have a much smaller pool, but it gets divided differently. You have about 35% going into grain. So you have first of all, you also have a smaller pool, significantly smaller pool. This pool can be as much as only perhaps 50 or 60% of the size of the other pool. So let's just say that each of these quadrants now represents 600 pounds. Or sorry, no, this 35% represents 600 pounds. So you have 600 pounds in grain, you have 600 pounds in the plant, and then you only have 300 pounds in each of these. So here again, you have 80%, that's 240. You have 60%, 300, that's 180. And then 20% of 600 is 120. That's not right. 120? And then, of course, this is gone as well. All right, so now you total these up. You have 540 pounds of organic matter being built in the soil from this crop that is not photosynthesizing well. And here you have 1,400, 1,600. You have completely different quantities of organic matter being stored in the soil profile. The only difference is how well these plants are photosynthesizing. And besides water, the second significant limiting factor that limits photosynthesis is carbon dioxide. All right. Thank you. So now, the next logical question becomes, if carbon dioxide is our biggest limiting factor, how do we get more carbon dioxide? I want to tell you a few stories about carbon dioxide. In 1977 and 78, there was a collaboration between 3 universities in the Midwest. There was Purdue University and the University of Iowa, and I forget the name of the university in Illinois right now. But they set out to conduct a 3-year trial to see if they took all of the best knowledge and the best technology of the day, how much would it be possible to push corn yields? What was the maximum potential that they were capable of with everything they knew at that point? So Don Huber was involved, who was leading the project at Purdue University, which is where I have the story from. Charles Tsai at the University of Iowa. Charles Tsai was the first biochemical geneticist to calculate the yield potential of corn. And he said that during this trial, he calculated that if they were able to optimize and supply adequate levels of water and carbon dioxide and nutrition to a corn crop, theoretically they should be able to produce 1,100 bushel per acre. So some of you may have heard me talk about that number before. There's now many other people who have replicated his work and say that his number is, if anything, is too conservative. But at any rate, they selected 11 farms through the Midwest. And in 1977 and 1978, they ran 2 crops. They ended up not going the 3rd year into 1979. Thank you. Because of funding issues. But in those first 2 years, they harvested the smallest harvest that they got on any of their fields on these 11 farms was 450 bushels per acre. So what's happened the last 40 years? Have we gone backwards or what? I asked Don the question, how were you able to produce those yields? And he answered my question indirectly. He didn't give me a direct answer right away. His response was, on every one of those soils, I could put my hand into the soil up to my elbow without any help. And what he was communicating, I realized afterwards, was not just that the soil was rich, loose, fertile soil, but that it had a tremendous capacity to release carbon dioxide. So, carbon dioxide, the biology in the soil breathes and respires the same way that we do. They inhale oxygen and nitrogen gas, and they release carbon dioxide. So the air, when it goes down into the soil profile, is 13 to 16% oxygen and 400 to 500 parts per million carbon dioxide and 78+% nitrogen. When it comes back out of the soil profile, when the biology exhales it, now the carbon dioxide level is 20 to 30,000 parts per million. So this means in the early morning, carbon dioxide is heavier than oxygen, it's heavier than nitrogen. Its preference is to stay close to the soil surface. And then during the day, we have this blanket layer of, or in early morning, we have this blanket layer of carbon dioxide on the soil surface, and then it gradually moves up into the atmosphere where it's picked up by the stomata on the bottom of the plant leaf surface. And in a young cornfield that's at V5 to V6 stage of growth, if you have, in what is common for most soils today at their carbon dioxide release potential, they will suck all the carbon dioxide out of the air by about 9 or 10 o'clock in the morning. And the carbon dioxide levels in a growing cornfield will drop down to under 100 parts per million by 9 or 10 a.m. This means that for the rest of the day, from 10 a.m. until sunset, it doesn't matter that that plant has perfect water and perfect sunlight and perfect nutrition. Carbon dioxide is the limiting factor that is limiting photosynthesis. So, when the volume of carbon dioxide that a soil is able to release is determined by the depth at which that soil is able to breathe. So when Don was telling me that I could reach into those soils up to my elbow, he was telling me that these soils could breathe and they could release and produce a lot of carbon dioxide. So, here's a quiz for you. Why do you want to have high levels of organic matter? It's not just so that you can store water. It's not just so that you can have better soil flocculation and better water infiltration. All of those are good reasons. But from a crop production perspective, the reason we want to have high organic matter is so that we can lose that organic matter while the crop is growing as carbon dioxide, so that the plants can pick it up and can cycle it and putting it back into the soil. See, the reality is we should not be having a conversation about sequestering carbon. We should be having a conversation about cycling carbon. The larger a volume of carbon that our plants can cycle, the healthier they're going to be and the higher yielding they're going to be. That's what this whole conversation really is about. So that's a very long way around the circle of soil compaction. So let's talk a little bit about water use efficiency. There's a couple of different angles here, a couple of different factors that have a tremendous impact on water use efficiency, but perhaps the biggest one that is the easiest to change is the form of nitrogen that our plants absorb. So, you can look at any biochemistry manual that talks about the biochemistry of plant nutrition and plant physiology and look at the reaction for nitrogen conversion inside the plant. And it's very simple. When a plant absorbs nitrate nitrogen, NO3, to convert NO3 to amino acids requires, each molecule of NO3 requires 3 molecules of water. It's really straightforward. Each molecule of nitrate nitrogen requires 3 molecules of water. So, if a plant absorbs nitrogen in the form of urea, or in the form of ammonium, or even better in the form of amino acids, there is no water required. So it can absorb nitrogen in any other form, and there is no water required. So the degree of difference this makes depends, of course, on which crop we're talking about and what its nitrogen quantity requirements are. But according to Olivier Husson, who was the first one to point this interaction out to me, he said that crops which get the majority of their nitrogen in the form of nitrate versus other forms of nitrogen will require as much as 30% more water for the same amount of growth. So, this is a pretty easy entry and pretty easy step into producing some better drought resilience and to producing lower water requirement crops. So plants can absorb nitrogen in several different forms. One is they can absorb complete bacteria, and I'll talk a bit more about this. The second is they can absorb what I will generically refer to as organic nitrogen, and this organic N can be in the form of amino acids or peptides. There's different forms of organic N that plants can absorb. The next is urea. The next is ammonium, NH4. And the last on the list is nitrate, NO3. Now I have listed these in the order of plant efficiency. So if a plant absorbs nitrate nitrogen, it costs water and it costs energy. So for a corn crop, I'm using a corn crop as an example because it's been very well researched and studied. If a corn plant absorbs 80% of its total nitrogen requirement in the form of nitrate, then it requires 16% of its photosynthetic energy. In other words, that day, that 24-hour photo period, of all the sugar that it produced, it costs 16% of that sugar just to convert nitrate to these forms of nitrogen. That's a tremendous energy cost to the plant. Now, I commented earlier, I bet you've never heard that potassium can cause a yield drag. I bet you've also never heard that nitrogen can cause a yield drag, have you? But nitrate nitrogen costs plants energy. It's pretty incredible because we are used to thinking about we put on nitrogen and we get this tremendous growth response. But what's actually happening, we get long internodes, we get widely spaced leaves, we get a lot of growth, but we cost plants energy during that process. So the cost for the energy cost for a plant to convert ammonium is there, but it's very slight, a couple of percentage points. Urea is even less. But then we get here to the organic nitrogen, amino acids, and bacteria. When plants absorb nitrogen in these forms, not only do they not cost energy, but the plants actually gain energy. So this is why a pound of nitrogen is not a pound of nitrogen. Nitrogen is not all the same. So we looked at some of the fields this morning and we say, oh, there's no applied nitrogen. In a couple of the fields, there was no purchased nitrogen. Well, that doesn't mean the plants didn't get nitrogen, obviously, because they're getting nitrogen from somewhere. They might be getting it in much smaller quantities, but they're still getting some nitrogen somewhere. If that nitrogen is coming from bacteria, the plants actually gain energy from it and they grow faster. So if you think about this, sometimes when growers decide that they want to begin producing organic crops, thank you, they will start, instead of using liquid 32 or some other form of nitrogen, they will switch to using perhaps, let's say, liquid fish. But when you do the math, they might be putting on 20 or 30 or 40 gallons per acre of liquid fish, but the liquid fish is like 2% nitrogen. And you do the math and you say that the pounds of nitrogen coming from the liquid fish are just a fraction of the pounds of nitrogen coming from the liquid 32. How do those two compare? The answer is they don't. They don't compare in terms of the energy that they give to the plant. So what we've been able to determine is that, and this is a very general rule of thumb, but a pound of organic nitrogen in the form of amino acids, in other words, let's say from compost or from liquid fish, a pound of nitrogen from one of these sources is the equivalent, in terms of overall plant growth energy and yield, it is the equivalent of 4 pounds of nitrate nitrogen. So a pound of N is not a pound of N. It's not all the same. These different forms produce very different crop responses. But I want to talk a little bit about bacteria because over the last 70 years, since the introduction of soluble fertilizers, we've gotten into this mindset that crop growth begins in the spring. That we start in the spring, we go out and we put on nitrogen and phosphorus and potassium, whatever other fertilizers we want to apply, and we get this strong crop growth happening that spring from that applied fertilizer. But in reality, that isn't, first of all, that's not the way natural systems work. What happens in natural systems is that you have soil biology during the dormant period when there is less vigorous crop growth. You have the soil biology extracting minerals from the soil mineral profile and incorporating them into their own cells, and then plants feed on these bacteria. So there's been this fascinating research has been led by Dr. James White at Rutgers University. How many of you have heard of rhizophagy? Okay, a few of you have, most of you have not. So this is fun. This is a lot of fun. So rhizophagy, we have a podcast about this. We have a webinar about this. There's lots of places for you to find out more about this process. But the word rhizophagy essentially means root feeding. So what he's described in his research, this is a growing root tip. And outside this growing root tip, you have all of these little bacteria. And he has described how growing roots can actually absorb these entire bacteria. The whole bacteria go back into the root system, or they penetrate through the growing root tip, and they move back here into the plant, or into the rootlet behind the tip. And when they get to this point, the plant releases reactive oxygen species that are highly oxidizing, and they strip the cell membrane off of these bacterial cells. So now you have these naked bacteria that no longer have a cell membrane. And then these naked bacteria are now absorbed by the plant cells as an entire cell. So the plant cell absorbs this entire bacterial cell and uses it as a nutrient source. So bacteria are about, I always get these two numbers confused. Is it 16% or 6% nitrogen? Do you know? Come on, you're supposed to know the answer to this. I think it's 16%, if I'm not mistaken. So I think pure bacterial cultures contain 16% N, if I'm not mistaken. So this is a very rich protein source, a very rich nitrogen source for plants. But, and there's lots of interesting pieces that happen here. I'm going to go finish describing this process. So then, some of these bacterial cells survive this process. They move back into the roots. In fact, they migrate throughout the entire plant eventually. But when they move back in the root tip, from the root tip far enough, there's an accumulation of them. A whole bunch of them end up together in one spot. And that accumulation triggers the development of root hair. And these naked bacterial cells that no longer have a cell membrane now move out through these root hairs into the bulk soil environment. And the plant also feeds them. The plant gives them the exact combination of sugars and proteins that they need to reform their cell membranes. And in this process, the plant has also communicated to these bacteria to say, hey, I need more phosphorus, or I need more manganese. These bacteria move out into the soil environment, and they communicate that to all the rest of the bacterial and fungal population in the soil, and they all together start extracting the nutrients that the plant needs from the soil mineral matrix and accumulate them inside their cells, and then this whole process just repeats itself over and over. This means that plants are not vegetarians. Plants are farming bacteria the same way that we farm livestock. Isn't that amazing? But here's an really interesting part. When we feed plants fertilizers that are water-soluble nutrients, what happens when the water disappears? Nutrient availability disappears. If you're dependent on water-soluble nitrogen, water-soluble nitrate or potassium, the moment the soil dries out, your nutrient availability drops tremendously. This whole process works very efficiently in the absence of free water in the soil profile. I use a very specific phrase there, free water. So this is something that I was absolutely amazed to learn. When soil, as soil is in the process of drying out, when it first reaches the stage where if you crumble it up, it starts becoming dusty. In other words, it's dusty dry. At that stage, this varies, of course, depending on clay and sand and silt levels. But if you have, this is specifically for clay soil. When clay soil is dusty dry, it still contains 70% of the moisture that it does at field capacity. Can you believe that? It still contains a lot of water. But that water is not accessible to plant roots. And the reason it's not is because of soil film adsorbing to the soil particles. So imagine that this is a small clay colloid, and on that clay colloid we have this very thin film of water. I think it's something like 70 microns thick or something like that. It's this very thin film of water around the colloid. The film is so thin that to us the soil appears to be visually dry. Plant roots cannot access that thin film of water in clay soils, but bacteria can. In fact, bacteria live inside of it. So this whole process that I'm talking about with rhizophagy is not dependent on free soil water. You can deliver nutrients, deliver nutrition to crops in a drought when you have this system working. Michael talking about it, Chad Wall talking about our soil primer. Our soil primer application is intended as a fall application to build the microbial populations in the soil during the fall and the winter month periods so that we have this reserve of bacterially available nutrients that plants can tap into the following growing season in the absence of water. So when we look at some of these crops, we say, oh, there's no applied nitrogen. How does this work and how is this happening? The reality is that these plants are getting nitrogen from somewhere, and there's a high probability that they're getting it from bacteria, and bacteria can deliver those nutrients in the absence of abundant rainfall. Now, obviously, this year we have had good rainfall, but this is a very important point because one of the pieces that we've observed working with a diversity of farmers and different crops in many different regions around the country is that when there is a very wet year, our microbial approach to plant nutrition does not outperform the mainstream approach by as much as we've come to expect. But whenever there is drought stress, whenever there is dry weather stress, we blow away the competition consistently. And it's because of taking this microbial approach to delivering nutrients to plants. So this is why it's why our soil primer application has become our most popular product and our most popular application. Almost everyone that we work with uses it because of the crop response that they observe from it. And of course, it's a lot cheaper than buying nitrogen and potassium and phosphorus, and it works. Thank you.